Today we're going to start talking about using the remainder and factor theorems to solve different kinds of problems. It's not going to have quite the same scope that our last kind of part of the unit did, but we are going to take a look at some pretty cool ways that we can go through and use both the remainder and the factor theorems. So just to reiterate and refresh a couple of brief points, we need to remember that when we're describing the remainder and the factor theorems, this is really what we're talking about. And it kind of creates a circular argument, which is good because it's easy for us to follow. But at the same point, if it's written in Mathanese, sometimes it's a little bit confusing to kind of wrap your head around. But basically, these two forms state that given some polynomial f of x, if that polynomial is divided by a binomial in the form x minus a, the remainder will be equal to f of a. So we can evaluate the function at f of a, and that gives us the remainder if I was to do division by x minus a. Then we could say that if f of a equals 0, then x minus a is a factor of f of x. Because if you go back and think even to your elementary level education, if you divide something and get a remainder of 0, then it has to be a factor, okay? And then if x minus a is a factor of our polynomial f of x, then that polynomial f of x divided by its factor x minus a will have a remainder of 0, okay? So we're really just kind of using these big ideas to go through and solve the next series of questions that we're going to look at. So let's see what we got. So the first one that we have here says, if f of x equals 4x to the 6th plus x to the 4th plus 4, then what is the remainder when f of x is divided by x minus 1? Well, you might be thinking yourself, oh, remainders, that's easy. I can go through and do it the old way that we did it before, where I would go through and set it up with synthetic division and say, well, I'm dividing by x minus 1, so my synthetic divisors are going to be positive 1. And then I could go through and set up all of the coefficients that are in here, but now I've really got to remember that I've got some 0 placeholders, because it starts at x to the 6th, and then it skips x to the 5th, and then we have an x to the 4th, but then it skips x cubed, x squared, x to the 1st, so lots of zeros there. So you'd have to go through and remember, okay, well, we got 4, and then we got a 0, and then we got a 1, and then we have a 0 for the cubic, a 0 for the quadratic, a 0 for the linear, and then finally a 4 at the end, okay? And I'm trying to go through and find the remainder. So this is really what I'm trying to find. That's kind of a lot to go through and do. I mean, think about how many times you'd have to go through and say, oh, let's copy that down. Okay, well, that's 4, so that's 4, so that's 4, so that's 5, 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 so that's 9. Wow. Okay, that's a lot of just writing stuff down and a lot of zeros, okay? So let's not do it the old way. Let's go through and do it the new way. And the new way, we're going to use those factor and remainder theorems. So we're going to use the remainder theorem, okay? Because the remainder, when we have this function f of x divided by x minus 1, is the same thing as f of 1. So I can just go and evaluate the function at 1. So 1 is my input, and the function f is 4 times my input raised to the 6th power plus my input raised to the 4th power plus 4. Okay, so again, reminder, our input in this problem is 1. And I'll pick a color that will actually show up a little bit better. So we're just going to go through and use direct substitution here. So this is really a 1, and that's a 1. Okay, following order of operations, I do exponents first. So 1 to the 6th, fortunately for me, is just 1. 1 to the 4th, fortunately for me, is just 1. And then add another 4. So 4 times 1 is 4, plus 1 is 5, plus 4 is 9. So f of 1 equals 9. So my remainder is 9. And if you think about it, this you can pretty much come up with in your head pretty quickly and easily. This is a much longer way to go doing it. So in each one of these cases, do you end up getting 9 as the solution to the question you were asking? Sure, you definitely do. But we really want to try and emphasize at this point using the remainder theorem to go and do that, because it's going to be so much faster. All right, so using the factor and the remainder theorem, now we get to do some interesting problems. So this first one says, given f of x equals 3x squared plus kx plus 12. Ooh, kx, what does that mean? Well, k is just another unknown value. So if we're given this polynomial where we're kind of missing some numbers in it, and the remainder when f of x is divided by x minus 2 is 14, then what is the value of k? Well, this could get interesting, okay? Because we know that we're doing division. So maybe if we try doing division and just plug in what we know, that could be one way to do it. So if we're dividing by x minus 2, then we know that our 0 would be positive 2. So that could be our synthetic divisor, right? We could go and set up division. So it is written in standard form with coefficients of 3, followed by k, followed by 12. But I happen to know for a fact that the remainder, because it says when the remainder, what it is, so when we divide it by x minus 2, that remainder is 14. Okay, so I could try and take a look at this and figure out, well, what could it be? Well, I knew if I was doing synthetic division, I would copy down the 3, and 2 times 3 would be 6. And then k plus 6 would have to be some number, and that number multiplied by 2 would have to get me, what, 2? Because in order to get 14, this number would need to be 2. To get a number of 2 here, I'd have to multiply something by 2 there. So this would have to be 1. And then something combined with 6 would get me 1. Well, that would have to be a negative 5, right? So if k was negative 5, I would go and copy down this 3. 2 times 3 is 6. Negative 5 and 6 is 1. 2 and 1 makes 2, and 12 and 2 makes 14. Yeah, that works. But you see how like confusing that is, trying to go both forwards and backwards doing our division? What would be a better way to do that? Okay, better way would be to use the factor and the remainder theorem. Okay, so we know that when f of x is divided by x minus 2, the remainder is 14. So essentially what we know is we know that f of positive 2 equals 14. Okay, we know that. So what is f of x? Well, it's the 3x squared plus kx plus 12. But don't I kind of already know what x is? Sure, so couldn't I just go through and kind of like plug that in? So I could do 3 times 2 squared plus k times 2 plus 12, and I know that that's equal to 14. So now I only have a variable of k that I can solve for. Easy, right? So 2 squared is 4, so I have 3 times 4 plus 2k plus 12 equals 14. So 3 times 4 is 12. So 12 from right here, and this 12 is 24. So 2k plus 24 will equal 14. If I subtract 24 from each side, I would get 2k equals negative 10, and then divide both sides by that 2, and I would get k equals negative 5. Well, isn't that kind of what I came up with over here, kind of trying to think my way through the problem awkwardly? Yeah, okay. This way was a whole lot more efficient though, and I didn't have to think forwards, backwards, and every in between, okay? We want to be thinking more like an elevator. We want to be thinking less like a Wonkavator. And if you don't get that reference, oh boy, go watch Willy Wonka and the Chocolate Factory, but the original one, not the really creepy new one. Brr. But anyway, what we did here is we used the factor and the remainder theorem. Okay, we know that f of 2 will equal 14 because that's what the remainder theorem tells us. Okay, so then by using the known value for x and what the function is equal to at that value of x, we can isolate a variable that's located anywhere inside of here and go and solve. Okay, so let's take a look at another one. So let's keep talking about using the factor and the remainder theorem on the next example here. So given f of x equals 3x cubed minus 2x plus k, and x plus 2 is a factor of f of x, then what is the value of k? All right, so again, let's try and use the factor and remainder theorem to go and do this. So when we see this right here, this x plus 2, and we've been told that it's a factor of f of x, we've also been told that the value of the function at -2 is equal to 0. So kind of like in the last problem, as soon as we make this connection and have this level of understanding, then we can take this function and use this little tidbit of information here. All right, so if f of -2 must equal 0, then we can say that 3 times -2 cubed minus 2 times -2 plus k has to be equal to, you guessed it, 0, because this is the value of the function when x is -2, and we know that when x is -2, the value of the function equals 0. Haha. So, order of operations. -2 cubed is -8. So this is 3 times -8. This becomes minus still 2 times -2, and we'll simplify it all in the next step. And then plus k equals 0. Positive 3 times -8 is -24. -2 times positive 2 is a positive 4. And then plus k equals 0. So getting k all by itself, we're going to end up with -20, combining those like terms, plus k equals 0. Then we'll get k equals 20. Okay, so if k is 20, then f of -2 will still equal 0. All right. Now, how else could we go and do that? Okay, we could also go through and use what we've already learned about synthetic division. Okay, if we know that x plus 2 is a factor, then we could also go through and kind of do some synthetic division. But because we know it's a factor, we know it's going to have a remainder of 0. Looking at the coefficients, I do have one that I'm skipping. Okay, I have a coefficient for my x cubed. I don't have a coefficient for x squared, so that's got to be a 0. My coefficient for x to the first is -2, and I don't know what k is. But because k is on the end, this might actually be a little bit simpler for you guys. But I really do want you thinking about how to use the remainder in the factor theorem. Okay, but if I did synthetic division knowing I'm going to get a remainder of 0, I would copy down the 3. -2 times 3 is -6. 0 plus -6 is still -6. -2 and -6 is a positive 12. And then -2 and 12 gives you a positive 10. So -2 times 10 is -20. And what we have here is we have another algebraic problem that you could go and solve. That you would need to go through and say that, well, if I have k and I take away 20, that equals 0, which kind of looks like that line over here, then I know that k would have to be equal to positive 20. Okay, so again, it's kind of two ways that you can think about it. This way is using more kind of synthetic division and what a remainder of 0 means. This way is implying all of that, but in a more algebraic sense. Okay, so let's take a look at another type of problem. So if f of x equals x cubed plus 12x squared plus 47x plus 60, which of the following is a factor of f of x? Well, the old way, if you were going to go and do it, how many times do you have to do synthetic division? Probably 4. Because you'd have to go through and see, well, does this one give me a remainder of 0? Does this one give me a remainder of 0? Does this one give me a remainder of 0? Does this one give me a remainder of 0? Okay, but there's an easier way to go and do it, and that's using the factor and remainder theorem. Okay, so we can just do some base substitution, and that will help us figure out if it's a factor or not. So the first one, our binomial that we're checking to see if it's a factor, is x minus 3. So that means that for this one, x would need to be equal to 3. So I can just evaluate my function at 3. So that means that I have 3 cubed plus 12 times 3 squared plus 47 times 3 plus 60. And you know what you can do to do a problem like this? Just grab your calculator, okay? If you just type in 3 cubed and then plus 12 and then in a set of parentheses 3 and then square that, and then plus 47 times 3 and then add another 60 to it, you're going to see that you get 336. That's a big number. It's not 0. So is x minus 3 a factor? Definitely not. Okay. The next one, we're going to check x plus 3. So if the factor is x plus 3, the 0 would be negative 3. So just evaluate the function at negative 3. So that's going to be negative 3 cubed plus 12 times negative 3 squared plus 47 times negative 3 plus 60. And I'll go ahead and tell you, I got a better feeling about this one, because the last one, everything was positive. It just kept adding and getting bigger and bigger. This one, it looks like it's going to alternate. I'm going to have a negative, then a positive, then a negative, then a positive. Maybe that'll all sum to 0. Who knows? So I'm going to grab my calculator and do negative 3 in parentheses cubed plus 12 times negative 3 in parentheses squared plus 47 times in parentheses and negative 3 and then plus 60. And I hit enter and ooh, I do get 0. So this one works out. So I'm going to go ahead and pick that one. Okay. To show you what the other ones would look like, just in case you wanted to see, over here I would be going through and saying x equals 4. So I'd be evaluating the function at f of 4. So that would be 4 cubed plus 12 times 4 squared plus 47 times 4 and then plus 60. And kind of like the first one, you can see that all of those are positives and not going to be something where you're going to end up with a 0. But if you wanted to go and type it into your calculator, then you would end up with something along the lines of 504. Okay, so you're just getting further away from 0, and you could kind of imply that if on the last one you were going and saying, oh, well, what about when x equals positive 5? It's going to be further away from 0 than 4 was. Okay, so instead of having to go through and do synthetic division 1, 2, 3, or 4 times, we can just do one simple use your calculator, evaluate, and call it a day. All right, so let's take a look at one more type of example. So this one is kind of hearkening back to all of the stuff that we've already covered, but we're going to do it a little bit differently this time. So it says if f of x equals 2x cubed minus 2x squared minus 8x plus 48, and x plus 3 is a factor of f of x, then find all the zeros of f of x algebraically. Okay, so if I know that this is a factor, then I know that f of negative 3 will equal 0. So I know that negative 3 will generate a remainder of 0. And really now it looks like the same sort of stuff we have on the quiz. Just want to make sure that we all still remember how to do this. So our coefficients, since everything is in order, are 2, negative 8, and 48. Okay, so if we go through and do our synthetic division the way it's supposed to be done, copy down that 2. Negative 3 times 2 is negative 6. That's going to give me a negative 8. Negative 3 and negative 8 is going to give me a positive 24. So this is going to give me a 16. And negative 3 times 16 is going to get me a negative 48. So I do have a remainder of 0. So what do I have left over? Well, in factored form, I have a factor of x plus 3, and that one was kind of given. And then from synthetic division, I still have a 2x squared minus 8x plus 16. Okay, I'm also going to notice that for this, I have a GCF of 2. So I'm going to go through and leave the x plus 3 over here, but I am going to go ahead and factor out a 2 because it's going to make the rest of my factoring or my quadratic formula that much easier. So this is just x squared minus 4x and then plus 8. So are there factors of a positive 8 that add up to negative 4? Not really, okay? So I couldn't exactly go through and factor that, but what I can do is your favorite thing in the whole wide world. I can use the quadratic formula. So for this part over here that's just in green, I'm going to have x equals negative b, which is really positive 4, plus or minus the square root of negative 4 squared, which is 16, minus 4 times a, which is 1, times c, which is 8, and all of that is going to be over 2 times a, or 2 times 1. So going through and doing just what's inside the parentheses, if I have 16 and I take that away from 4 times 1 times 8, that gets me a negative 16. So I have 4 plus or minus the square root of negative 16 all over 2. Well, the square root of negative 16 is really 4i. So it becomes 4 plus or minus 4i all over 2, which of course can be simplified. So my solutions for all of this, or all of the zeros algebraically, are that x will be equal to negative 3, and then also 2 plus or minus 2i, because half of 4 is 2, half of 4i is 2i, so that's where that comes from. Some people always ask, well, what about this 2? Okay, that 2 is a factor, but it doesn't have a variable. Because it doesn't have a variable, it can't really be part of the solution, okay? So it's just kind of hanging out over there. Had we left it in with all of this, these numbers would all be bigger, but they would have all simplified down to just 2 plus or minus 2i at the end, okay? So today we've talked about a couple of different ways that we can use the remainder and the factor theorem to evaluate parts of a polynomial, especially when we're given either zeros or roots or factors. And then we've also reviewed how to go through and find all of the zeros given a factor or a zero.